So we'll go ahead and get started, but I did want to remind you, like I said, the first day of, if you go to your online classes, this class is under there. So if you miss a lecture here and there, this actually is a good way to authentication required. That's me, I promise. Really? Okay. Anyway, it would look like this is what I was trying to show you. This isn't through the portal, but actually this is if you go twitter.com/EA Snipes_CHM122. So, yeah, I posted this. I thought this was cute. We talked about how, like, if you dissolve something in water and it's an ionic compound, basically it breaks apart oftentimes. Like sodium chloride will break apart. And so sodium chloride, there would be your little blue would be your sodium and your green would be your chloride ion. So they're together like in their solid state, and then they dissolve in water and they just go, oh, it's like, I'll never forget you. So these are water molecules surrounding them. Anyway, so that's out there. But so like if you miss a day and you're like, well, I wonder what she assigned. Actually, I post my assignments up here. So for instance, you usually do. And do Friday, yeah. This is the one you guys handed in right now, right? 5862. It's been one of those weeks.
Well, I thought
she was walking with a thing of donuts.
Get donuts in case anybody wanted a donut. And there was like a ridiculous line at Casey's. So help yourself if you want a donut.
Anybody want a donut?
I don't like donuts. Is that weird?
That's kind of weird. You don't like chocolate, you don't like donuts.
I needed sugar, so I'm like, I'll share it with donuts.
I might grab one on your way out.
That's fine.
So that's all there, guys.
Anytime we're trying to do something nice, it's like everything has to be nice.
Hey, is that fire truck going?
No.
Oh, okay.
And that too, I'm like going 5 miles per hour.
No, I thought they pulled me over. I was telling her, I was like, oh my god, what did I do? Like, I didn't do anything. I never had a ticket. Well, and then there was this old guy, I was like, are you okay? Like, because he was like showing them where to go. These cops get out and start running. I'm like, a lot of times if I was a student, I'd like to know what we're covering, and I do it to remind me what we're going to do. I toyed with going on into the next part, but I just want to finish part 5. There are 2 assignment slides in part 5, and part 5 is kind of like what you guys did in lab yesterday. So we're going to start here, kind of pick up where we left off on Wednesday's lecture. So density is what you guys did yesterday, is come up with the density of 2 objects, and what you did was take the mass and you divided by the volume. Okay? And you came up with density of a block and density of a rubber stopper. Now I want to spend just a minute talking about density of H2O, density of water. So it depends on if water is a liquid, if water is a solid, or if water is a gas. A little bit. The density of the gas is going to be very low. You know, the density of the solid you would think would be kind of high, and then it kind of works that way a little bit. But water, I said, you can go with a density of 1. And the units would be grams per milliliter. So if you were to take 1 milliliter of water, it would weigh 1 gram. Okay, that's kind of how that works. Before we move on, remember that if you were to fill in these blanks, what goes in those blanks? 1, the number 1. Okay. Volume, you can actually talk about milliliters of volume. You can also talk about cubic centimeters as volume. Okay. All right. So usually, the colder something gets, and I'll draw your attention to the bottom there, okay, as you go from right back to left again, it's getting colder. You buy that? There's getting colder. Usually as something gets colder, it gets more dense. Okay, so here we got water. This is the density of water liquid water, as it gets colder. Okay, it's more and more dense, right? Now, water, as it gets ready to, water freezes, by the way, at 0 degrees Celsius. As water gets ready to freeze, it actually, as it gets colder, it gets fluffier. This right here is unique for water, for the compound water. Okay, so as it's getting colder, it's actually getting ready to crystallize, form snowflakes, that sort of thing, kind of. And so here, its density is decreasing, which is weird as it's getting colder. Well, right when it transitions from liquid to solid, okay, right at 0, it actually makes a humongous jump. So down here, as water is a solid, okay, notice that its density jumps that much. Okay, its density decreases. So this is less dense, which is not the way normal substances go. Normal substances transition from their liquid to their solid just fine, getting more and more dense. Or, getting more and more dense instead of taking that jump to being less dense. This right here, this big jump right here has to do with it's forming crystals, ice crystals. And ice crystals has to do with what we call hydrogen bonding, H bonding. Okay. So one last thing about this. So ice, on the Earth, we have a large amount of Earth's water is tied up in glaciers. Okay? And the deal about ice is, since it's less dense, ice will float, F-L-O-A-T, in liquid water. Okay, so you know that when you get like ice water, your ice cubes float. If that liquid were like carbon tetrachloride and you made carbon tetrachloride ice cubes, those ice cubes would sink. Don't have to be that exotic. If your water, and this is kind of fun, if your water was not H2O, but if it were what we call D2O, H2O is water. Hydrogen, there's some different versions of hydrogen. One of them is deuterium, you may have heard of before. Deuterium is just a hydrogen atom that it's heavier, okay, it's more rare. So if instead of your hydrogens, if you substitute deuterium, which is another form of hydrogen, okay, then actually those ice cubes would actually sink in regular water, not deuterium water. Got myself to thinking there. Anyway, so I just think that's cool. We're glad that ice floats. I was going to finish that thought. If glaciers would sink, then actually they would displace the water that they're sinking into, and Earth has a hard enough time with finding land. Like we only have like a third or a quarter of our whole surface of the Earth as land. So we don't want ice to sink.
Have you ever added salt to water and then put an egg in it and it floats? Is that density stuff?
Yeah, that is density stuff, yeah.
Because that's like, my dad does a lot of smoking meats, and the brine you use, you just add salt to the bucket until the egg floats, and then you know it's good for your meat.
Well, that's neat.
Yeah.
I like that. Yeah, that would be a density thing.
When we were kids, my mom used to do, we would put a bowl of water, and then you sprinkled pepper on top of it.
Mm-hmm.
And you put dish soap on your finger and
Runs away.
Uh-huh, I love that. Run
I don't know
away.
what it is, but me and my brother used to get a kick, or like food coloring, it does the same thing.
That's cool. Yeah, that's polarity. So, yeah, your water is very polar and your pepper is very non-polar. Or your your pepper is the detergent is what kind of makes it sound. So these two things are kind of similar volumes. The guy's holding them in his hand, similar volumes. But which one would weigh more? Yeah, the rock. So if we said, if you're going to come up with the density of either one of those, you would take the mass divided by the volume, and since their volumes are the same, okay, but the mass of the rock is higher, basically you're going to get a higher number for density. The density of the rock is greater. All right, we have 3 substances here. Which one is the least dense? Styrofoam. How can you tell? Because it's floating, exactly. So kind of quick and dirty, you can see the rock is more dense, and the water must have a density between the rock and the styrofoam. So all at once, you can get that. Density is a physical property. You don't have to do any sort of chemical reaction. You just got to measure its mass and volume. So, all right. So this is a table that you might use for your homework. There's the density of a few objects. Notice this density is given in grams per cubic centimeter, kind of like your density for your wooden block. But actually grams per cubic centimeter is the same thing as grams per milliliter, because cubic centimeter and milliliter are the same. Down here, these are all elements. Okay. Glass, generally I guess I'd call it a compound. And I guess these others, these are compounds, CPD for compounds. Charcoal, I'd almost call it a kind of a mixture. I don't know. That's what I think of it, because I think it's got different chemicals in it. All right. So here's your assignment. We'll take a look at these real quick. That's not too bad. One of the things, like what you guys did in lab yesterday, is you made sure you showed all your work, you made sure you used units, and you rounded correctly. Okay, and that's kind of the theme of what you're going to be doing here too. So 95 looks like this. A sample of an unknown metal has a mass of 35.4 grams and a volume of 3.11 centimeters cubed. Calculate the density and then compare the density you come up with this table. So it's not too bad. It's kind of like what you guys did in lab. The mass and the volume are given. Be sure to show all work and round correctly. And then the next one is kind of similar. Whoops. The next one looks like this, where it says you have a new penny, and again it gives the mass and the volume, and it asks if this is pure copper. And it doesn't say to, but I would refer you to the density of copper. What do you think? Are the pennies these days pure copper? No, I can't remember what they're mixed with, but they're not pure copper. Yeah, so anyway, that's kind of that. Okay, so on to the egg, right? So what you guys did yesterday was to come up with a weight percent of shell, white, and yolk, okay? And I like to kind of say by definition, if somebody gives you a weight percent, and we'll be using problems kind of like this. If somebody, for instance, says, let's take the penny for a minute. Let's just say somebody says that is 95% Cu, 95% copper. What they mean is that if you have 100 grams of the mixture, which would be the whole penny, 100 grams of penny, that's the mixture because we're saying it's not pure copper, it would contain 95 grams of copper. That's what it means, kind of by definition. That's kind of unpacking it. Okay? But like in lab yesterday, you didn't have 100 grams of egg. You had a certain mass of egg, and all you did to come up with the weight percent was this. In the bottom, you put the total mass of the egg down here. This is the total mass of the mixture. And in the top, you put the mass of the component of interest. Okay? And then to get it into parts per 100, you multiplied by, sometimes I put 100%. You multiplied by 100 or 100%. And when you were doing this, actually, your units of grams, and we'll talk more about canceling, your units of grams actually canceled out. All right. So mass fraction is very similar to mass percent. Mass fraction, almost, it's going to be the same number, but basically it's going to be, the decimal is going to be moved over 2 places. So if somebody, we can pick on that penny a minute ago, what did I say, 95%? Okay, good. So for that penny that was 95% Cu, mass fraction would be 0.95 mass fraction. I should put Cu, 0.95 Cu mass fraction. See how that works? So kind of by definition then, we would say that if you have 1 gram of penny, you'll have 0.95 grams of copper, based upon that information. All right. So kind of like, well, if you were tasked with coming up with not the mass percent, but the mass fraction, it'd be very similar to their mass percent. You would go isolate, get a fix on your total mass of your mixture. You would get a fix on the mass of your grams. The only difference here is you don't multiply by 100%. That's the only difference. That's totally it. It's missing that multiply by 100%.
So if we had a problem like this, or a question, homework problem, whatever, will they let us know to the decimal places that we need to be at? Because like when we did the percent of the egg, we knew what our significant figures or our decimal places had to be at.
Right.
And it was way past that when you get your calculator answer.
Right.
So,
And with mass fraction, it would be similar, because when you do it, you're going to be doing this division. You're going to say, oh, I'm dividing, so I need to round according to significant figures again. So it'll be the same. Yep. Yep, yep. Okay. So sometimes I draw pictures, sometimes I don't. Sometimes they're kind of overkill. But just for kicks, here's my beaker. Okay. Now we're going to make a solution. And notice we're going to put 5.42 grams. The thing about a picture is it can actually kind of help you work the problem sometime. 5.42 grams of sucrose. And it's also then going to have 28.72 grams of water. Okay, I'm going to mix it up. Okay, so do you buy this, that actually my total, the mass of my mixture is going to be this plus this. That's my mass of my mass of my mixture. And actually that's one of the things I'm going to do to come up with the weight percent of sucrose. So you got to make sure you show all of your work. Now down here at the bottom it says knock out the mass fraction and the mass percent of sucrose. We can do that. So there's kind of slightly different ways to work this maybe, but I'm going to kind of show you how I think works well. So the mass fraction is basically the mass of the sucrose, the thing of interest, divided by the total mass of the solution. And I'm sure you guys know how to get the total mass of the solution. You add those two together. So one of the things, and I'm going to show you it preferred here, I would like to do as a separate problem that little addition. And part of the reason I want to do this little addition to come up with the total mass of the solution aside is that then I know how to round it because I'm adding, and it's going to go back to decimals. So the mass of the sucrose was 5.42 grams. The mass of the water was 28.72 grams. And since we are adding, we have to round according to decimals. So I have 2 decimals here, 2 decimals here, and actually my calculator displays 2 decimals, and I'm going to keep both of those decimals. You know, if we compare that to the rules for multiplication and division says I would round according to sig figs, and I would end up with 3 sig figs, and that's not right. Okay, so that's the number that's going to go on my bottom, and then I go ahead and knock it out. Mass fraction would just be the mass of the sucrose, 5.42 grams, divided by the total mass, which is 34.14 grams. Okay, and we decided since it's mass fraction, not mass percent, that I'm done. And we'll talk more about this on next week, but I think I mentioned if you have grams, you can actually cancel out those grams. So it's what we call unitless. So now we're going to round according to decimals or significant figures. Sig figs, and how many sig figs? 3. Perfect. That's it. 0.159 mass fraction. So what would be the mass percent then?
15.9%.
You got it. 15.9%. 15.9% would be the weight percent.
When you go to show that, because I already did it, I just put times 100 for mass percent,
Yeah, that gets it. I always pause. Sometimes it's easy to know how to show your work, but I think if you just took 0.159 times 100, or times 100%,
Yeah,
Yeah.
and I just put times 100.
yep, yeah, I think that would be good. Yep. Always show your work. So if we have 0.159 mass percent, we could unpack that. And what that means is that if you have 1 gram of the solution, you are going to have 0.159 grams of sucrose for that particular solution. All right. So, yep, the mass percent would be 15.9%. And yeah, I'm a stickler for showing your work. And how would you show your work? Maybe just show, like we said, 0.159 times 100. And it kind of makes sense because, we don't do a lot with like scaling up ratios here. But if you were to scale up the 1 gram in the previous one, okay, to 100 grams, then you have to scale this up times 100. So that's kind of how that works. Cool. All right, I think I have one more problem. There's this one. And we'll go ahead and draw a little beaker. You wouldn't have to do this, but like I said, sometimes a picture's like, oh yeah, that I can remember, or it might help you get the right answer. So this one is the solute is sodium chloride, not sucrose, and it's 8.18 grams of NaCl. And then we have, this is just like the little picture we saw starting out class. The sodium chloride's dissolved in water. And then the amount of water is 101 Dalmatians, 101.50 grams of H2O. It's very similar to the one we did before. We're supposed to knock out both the mass fraction and the mass percent of NaCl. Okay, so we're going to add those two together. It's going to be in the bottom, and then we're going to divide, and we're going to come up with the mass fraction and mass percent. So, again, I really think if you go ahead and calculate the total mass of the solution, it really can you're less likely to make a mistake. So the mass of the NaCl, 8.18 grams. The mass of the water, 101.50 grams. Since we're adding, we're going to round according to decimals. So the total mass of the solution that's going to go in the bottom is 109.86 grams. So we're ready to go ahead and knock out our ratio to get to the mass fraction. And so that would be the mass of the NaCl, 8.18 grams, divided by the total mass of the solution, 109.86 grams. And since now the mathematical operation is division, we're going to round according to significant figures. I got 3 sig figs here. Sometimes I'll put little check marks. 3 here. I got 1, 2, 3, 4, 5. I got 5 down here. I always have to go with the fewest. So that's why I have to round according to 3 significant figures, regardless of what my calculator displays. So picking 3 significant figures, this 0 right here is a leading 0 after the decimal. It does not count. So there's our 3 sig figs. So that's the mass fraction. Then to get it to percent, we just multiply that by 100. And so 0.0746 times 100 is 7.46%. Not bad. Any questions about that one? Again, it's a physical property, but do you see where weight percent it's a physical property that can really vary depending upon how you make up your mixture. Okay? All right. So, here's the assignment. Yep, it's in Chapter 13. Don't you feel like you slept at a Holiday Inn last night? Chapter 13 deals with solutions, but I do want to say something about it. I went ahead and brought up 41. Now, right off the bat, you guys know that you can get the answers to those odd problems in the back of your textbook, okay? You're supposed to come up with the mass percent in each of these cases, so it's similar to what we were just doing. I do want to make an important note, and if you want to write this on your slide, I want to pick out this, I think this is glucose right here, because later on, pretty soon, we're going to talk about how do you get from milligrams to grams. We haven't talked about it yet. So for B, let me just go ahead and tell you that C6H12O6, you guys probably tell me already. Milli means 1/1000th of, and we're gonna have to do this more fancy than this, but it's 0.178 grams of C6H12O6. Okay, so you want to have the same units, so it'll work out. Okay, any questions? That's as far as I wanted to get. Next week, all lectures are important, but when we talk about factor label, it will be good to tune into that. So bring your calculators next week too if you want. Kind of work problems as we go. Okay. Have a great weekend. And there's still donuts back there.